right, this is the continuation of the section 3.4 notes from class, looking at just some different variations of some of the examples. So we're going to start off with the first example that had us evaluating f of a, f of a, negative f of a plus h, f of a plus f of h, and then this is, remember, the difference quotient. We kind of talked about that. So we're going to do that with this second function here. Now notice this is a little different because there are two x's instead of one. So we will be plugging in anything that we do into both locations, because when you plug in f of, say, a number, f of 2, you plug it in for all the x's. So we're going to be doing the same thing here. So let's look at, let's change colors to maybe this purple color. Let's start off with the first one, which is f of a. And that's just straight substitution. X turns into the letter A. So that's going to be 2a squared plus 3a minus 7. Nothing we can do because none of those are like terms. The second evaluation we were supposed to do was f of negative a. When you plug in a negative a, it's very important to put it in parentheses so that you can evaluate it, especially if there's like an exponent. We need to make sure we take care of that first. So if you square a negative, you're going to get a positive. So that's just going to end up staying 2a squared. If you multiply negative a times positive 3, you're going to get negative 3a, and then you have your minus 7. Again, no like terms, so nothing we can combine. Then we had negative f of a. This means negative 1 times our original function with the a already plugged in. So that was the answer to that first part, 2a squared plus 3a minus 7. We're going to multiply that by the negative 1, so that's negative 2a squared minus 3a plus 7. Okay, and then we have f of a plus h. This is a binomial going in for a single variable. So when you plug that in, everywhere we had an x in the original equation, we're going to plug in a plus h. So notice it goes into both x locations. For this first one, we're going to have to FOIL that out. So that's going to be an a plus h times an a plus h. For the second one, you can go ahead and distribute that 3. So that's going to be a 3a plus a 3h. Go ahead and bring down the minus 7. I would FOIL out the two binomials first before distributing the 2. This will always work out to a squared plus 2ah plus h squared. And you can check that, but that's how the same binomial twice would FOIL, especially with a plus in the middle. And then we distribute that 2, so that's 2a squared plus 4ah plus 2h squared, and then bring down all of the other terms. So plus 3a plus 3h minus 7. None of these are like terms. We can't combine any of them together. Okay, then we get into the evaluation, and I'm actually going to draw a separator from the previous problem. We had one where we did f of a plus f of h. This is just two separate function evaluations. So the first one is the function with a instead of x. So there's f of a. The second one is h instead of x. So 2h squared plus 3h minus 7. We can't do much to combine the like terms here except for the minus 7s. That's the only ones that are like terms. The others don't have matching variables or exponents. So we'll get a minus 14 at the end. Now the last part for this one was that difference quotient. We had f of a plus h minus f of a all over h. Now I'm going to highlight, we had already done f of a plus h. Give me just a second. The highlighter doesn't want to work on this part. Oh, I forgot. So we are going to use a color and underline. So let's do blue. So the f of a plus h was this answer right here. Okay, we're going to substitute that with that. And let's use maybe red. The negative f of a was right above that. So we're going to use substitution right there for that. So once you've done those two pieces, obviously you're just plugging them in and simplifying the fraction. Now, if we hadn't done those pieces yet, we would have had to do this evaluation and then this evaluation and then put it in for our numerator. But we've already done all the work. So the answer for the f of a plus h was 2a squared plus 4ah plus 2h squared plus 3a plus 3h minus 7. For the second part, we had the negative 2a squared. I'm going to have to write a little bit underneath this, minus 3a and plus 7. And then all of that is over h. Okay, if we find any common factors, we can cancel those out on top because they would be like terms that cancel each other out. So the 2a squared and the negative 2a squared, the 3a and the negative 3a, and the negative 7 and the 7. That leaves us with 4ah plus 2h squared plus a 3h all over h. You can factor out an h on top of each term, and then that would cancel with the h in the bottom. So that leaves my final answer there. I'm going to write it right here underneath, is 4a plus 2h plus 3. So that's on that page. All right, so that one was a little bit more complicated just because there were 2 x spots, but the idea of what we did in the first example, it still carries through. It's just plugging in the part in the evaluation in the parentheses for your x's and working out what you can. Okay, the second one that we skipped over was another find the domain and range from the picture and then answer these questions about the ordered pairs. So if we look at this one, and again, I'm going to do color coding. We'll keep it to the same as before. We'll do domain in blue, and we'll do range in red. So when we talk about the domain, we're talking about in our function picture right here, what's the list of x values that are being used for the ordered pairs. So the farthest left I see any x values being used is -5. And then the farthest right, it looks like it would be, and I even put the point here for you, it's at +7. There's no graph on the x-axis. There's none of this graph below this point or above this point. And every single point is included in between. There's no open circles. There's no weird gaps. All x values, even their decimals, have been included somewhere as part of this graphing that they did. So this would be, the domain is -5, since the endpoint's included. It'll be a bracket up to 7. So there's the domain of that one. Then for the range, we're looking at the y-axis values. So let me get the red. There we go. The lowest my graph ever goes on the y-axis, and I always look left and right, making sure there's no points down here. The lowest we ever go is at -1. The highest the graph ever goes on the y-axis looks like it's at +2. So we can verify that with those points that we see. So every single point is used in between. I can pick any point I want in this little region, and I can find a point on the graph that corresponds to that, either to the left or right of my y-axis. So, and we are including the endpoints again. There's closed circles. So this would be everything from -1 to 2. Our whole graph is squished in between that y value range. So that is our domain and our range. So let's talk about what do we do for the question that was up here. Find f of 1, and then find all x's such that f of x equals 1. So if you're looking for f of 1, this is an x value. You're looking for the y value that goes with it. Okay, so anytime they give you the number, they're telling you this is x, find y. So I go to my x-axis and find 1, and I find that point that's attached to that. So that means the y value there is -1. This is a little different. This is saying my y value that they gave me is a 1. Find the x's that match. And because to be a function, the x has to be unique, but not necessarily the y, this is going to make it possible to have more than one answer. So if you go to 1 on your y-axis and you kind of just draw a dashed line all the way across, you'll notice we cross our graph 4 times. So there are 4 x values that give us a y value of 1. We had -3 because they've actually listed the ordered pairs there for you. -1, 3, and 5. Okay, so so let's talk about the one, there was two we skipped on the implied domain part. Mainly this one because it's harder than anything we would give you in a test situation, but this one we did together. We said that, remember, the implied domains, depending on what type of function it was, polynomial, rational, absolute value, odd root radical like a cubed root, or an even root radical like a square root. If you have an even root radical, you have to keep the interior part, the radicand, that's what it's called, underneath the radical, greater than or equal to 0. That's so that we don't get imaginary solutions, we stay real solutions. So if you try to use this one, it's got a polynomial bigger than an x to the first. So anytime you have an x squared or higher in an inequality, we're doing those sign charts we learned about in section 2.7. So we're going to factor that into x plus 5 and x minus 5 and set that greater than or equal to 0. Two critical values then would be -5 and 5. Remember, we make a chart, number line chart, with -5 is the smaller number, 5 is the next number. These are both equal to, since this is numerator, we don't have to worry about weird things about open circles. This is -infinity to -5 bracket, bracket -5 to 5 bracket, and then bracket 5 to infinity. We're going to pick test values in each region, and then remember, plug those into our factors. So x plus 5, x minus 5. We hope that the overall sign is greater than or equal to 0. So I could pick -6. Remember, it has to be in the interval. So -6 is to the left of -5. We could pick 0 and +6. This would give me a negative and another negative. Two negatives multiply to a positive. This would give me a positive and a negative if I plug them into each one of those. That all multiplies to a negative. And 6 gives me two positives, which multiplies to a positive. Now we wanted, and I'm going to do this in a different color since I can't highlight on my ink, we wanted it to be greater than or equal to 0. So it's these two positive regions. So my domain for this problem right here is -infinity to -5 bracket union bracket 5 to infinity. So the question is, do we really believe that? Because, you know, sometimes people will look at these things and they'll say, well, how do I know if I did it right? Or how can I prove to myself that this method really works? And one thing I can say is to go to Desmos a couple times just to kind of ask yourself the question, did I get an answer that makes sense? And if you put in your graph, and let me make sure I'm actually sharing Desmos, yes. If you put in your graph, ours was the square root, and to put that in, I used the square root symbol by typing SQRT, and then we had x squared, I think minus 25 underneath our radical. So x squared minus 25. And what you'll notice in this picture is, look, the graph is nowhere in the middle right here, because I can scroll out, you can see it's going off to the infinities on these two sides. We have no graph between -5 and 5. We have graph everywhere from -infinity up to -5 and from 5 to infinity. So this sign chart method really does give us the correct values for our domain. So that is working out for us really well. Now, the only other one I didn't do in the domain of the function when you have it given to you was this last one. And the reason is it's the same as D. The only thing they changed is they put the square root in the bottom. That changes one specific piece of how we solve it. And it's a minor change, but it is important. So I'm going to write my little steps here. I still talk about the radical part first, and then we talk about this second, just because this is a restricted value, a singular restricted value, and this has to do with members staying a real number and not an imaginary. If your radical is in the denominator, so if your even root radical is in the denominator instead of the numerator, we set the inside part greater than 0, not greater than or equal to. And the reason for that is we don't want to divide by 0. Trying to get my eyes dotted, by 0. Okay. Does not want to do a period. There we go. So the inside of the radical. So notice up here we did greater than or equal to 0 in part D. That's because the radical was in the numerator. It's okay for a numerator to equal 0. It's not okay for a denominator. So that's really the only difference. It's going to be an endpoint difference. So this is going to be x is greater than -3. So we know over here, we go ahead and start our answer and say greater than -3. So notice I'm using a parentheses. And here we do have one more restricted value. +3 would make that factor equal 0. So we need to make sure we don't include that. And since that is greater than -3, we do have to skip over it. Remember, we just do that by creating a union, and we start and end on that point with parentheses. That means we're only skipping that one number on the number line. Okay, so let's keep going. Now, this part right here is not on our midterm test, but it is a good thing to lay groundwork for some calculus later on. So we're going to be doing in this next section, we're going to be doing some graphing problems, mainly just talking about their domains as well. And then we're going to talk about if the graph increases, decreases, or stays constant. So if your x values are getting larger from left to right, and your y values are also getting larger, they're growing up in terms of their positive, positively getting bigger, then that means that this function is increasing from that interval, from that number to that number. And if your x values are getting larger, but your y values are getting smaller numerically, then we are decreasing on our interval. If our y values stay constant, don't change on an interval, then we say the function is constant on that interval. So it's not really that hard to understand it, but this is going to be important for like analyzing things later on in calculus. We talk about increasing, decreasing, and constant to try to figure out maximum and minimum points and things like that. So it is important for later, but like I said, not on our test. So what we're going to do in this little group here is we're going to sketch the graphs, and we're going to use different methods that we know, like table of values, or we can use slope-intercept form if we know that. We'll find the domain and range of the function, and then we'll find the interval on which it's increasing, decreasing, or constant. And it may only be doing one of those three directions. Not every function will do all three things. So that's why we want to talk about it on the intervals. And when you say find the intervals, these intervals are domain related. Okay, so it's going to be x values. So you're going to say from this x to this x, my y values are increasing, decreasing, or constant. Okay. So for this, let's talk about this. This is linear, so I can use my method that we learned in section 3.3 of plotting this as a y-intercept member and a slope. So rise over run. And if you don't have a run in the bottom, it's over 1. All integers are over 1. So 0, 3 is on the y point. And then we're supposed to go, this is down and then right. So down 1, 2, right 1. I usually do that a couple times so that I can draw a straighter line. So down 2, right 1, down 2, right 1. And if you know you don't have a ruler, you might want to do the opposite direction as well and get all of the points. So up to left 1, up to left 1. Sorry, I got off. And then we draw our line best that we can. Put the arrows on each end. So this is a linear equation with a negative slope. So notice it's going downhill. So the domain. This is a polynomial. There should be no restrictions to the domain. And if you notice, you can plug in any x you want into this function and get an answer. So it's -infinity to infinity. The range is also all real numbers because if you look at this, there's no y value that wouldn't get used either. These are going down forever and up forever on these two sides. So linear equations don't have a lot going on sometimes when they're slanted. It's just all real numbers possible for both parts. Now, this function is decreasing the entire length of the x-axis. If we were to find more y values, we'll notice these are kind of higher, and as we go from left to right, they're always shrinking down lower and lower and lower. So this is decreasing on its entire domain. So decreases on the whole domain. Okay, let's look at the next one. And again, we haven't really learned any tricks about how to graph quadratics any differently. So we're going to just do a table of values. So we're going to put this in, and I usually do -2, -1, 0, 1, and 2, just if I have no idea what to pick. Plug them in, so that's -2 squared minus 1, so that's 4 minus 1, that's 3. -1 squared minus 1 is 1 minus 1, that's 0. 0 squared minus 1 is going to be -1. And if you've got a good set of points, you should see some symmetry here. That's also going to be 3. So let's plot those. So -2, 3, and we'll learn more sophisticated techniques of graphing quadratics in our next unit. So 0, -1, 1, 0, and 2, 3. A parabola should have a U-shaped graph. And it's, again, a polynomial. So its domain is all real numbers. I can plug any number into that formula and get a real number answer back. The difference is, though, between this and a line is there is a lowest value on the y's. The lowest this graph gets on the y's is -1. So this is a graph that has a range that's -1 up to positive infinity. So only that part of the y values are being used. And these are both parentheses, by the way. And then for the increasing or decreasing, well, this splits. And again, you have to talk about it in terms of the domain, not the range values. So at 0, this is our x value where this point happened, where we kind of turned our direction. So from -infinity up to 0, our graph was decreasing. The y values were going downhill. So from -infinity to 0, we were decreasing. Once we got to 0 on the x-axis, our y values start growing. They started getting more and more larger. So we were increasing on 0 to infinity. We do not use brackets when we talk about increasing, decreasing, or constant, because when you're comparing increasing and decreasing, you're continually comparing 2 points at a time. So you shouldn't be having a stopping point on a single point. That's kind of how I think of it. So when we do these, we always use parentheses. And then there's 2 more graphs. Okay, so this one is a square root. Now you again could start plugging in any ordered pairs that you want, plug in your x and find your y, but we already know how to find domain from a square root. You just have to make sure this part stays greater than or equal to 0. So if I were to subtract over the negative or the 4, so that'd be -4, and then divide everything by -1, notice that's going to flip the direction of my inequality. So I can plug in any numbers I want as long as they are less than or equal to 4. And that makes sense because if I plug in a 5, I'm going to get a negative underneath that square root. So we can plug in 4 because that would give us the square root of 0, which is 0. We can plug in bigger numbers, or sorry, not bigger numbers, smaller numbers. So 3, 2, 1, 0. We'll see if that's enough to get the graph. So 4 minus 3 is the square root of 1, which is 1. If we do 4 minus 2, that's a square root of 2. I don't know if I want to graph that guy, but I'll write him down. 4 minus 1 is the square root of 3. Again, not a nice number. Probably won't graph that one. I just want to get 3 nice points. So square root of 4 is 2. Okay, so I can plot these 3 because these are nice. So 4, 0, 3, 1, and you could plot the other ones, but maybe not on WebAssign because remember it doesn't like decimal points on the graphs, and 0, 2. A square root function looks like half of a parabola on its side. That's kind of its general shape. So if you notice, that makes sense with the domain that we found. The domain here is -infinity up to 4. Everything in our graphs from -infinity up to 4 on the x-axis. The range, well, again, you look at your y values. There's no negative y values on my blue graph. I don't have any negative y values being used. I do have 0 because that's this point. And then people sometimes think this stops here. This is just slowly growing. So we don't really know how this is going to get higher and higher forever. It's just going to take a long time. So this is going to be from 0 to infinity. It will eventually keep growing up, just like parabolas spread out. Okay, and then is it increasing, decreasing, or constant? Well, this is continually sliding down the y values. So the y values start higher and they go down as we go left to right. So this is decreasing on its entire domain. Okay, and again, parentheses indicating we don't include that endpoint. All right, and then the last one, this guy, sometimes people will have a trouble graphing this because they don't know what it's saying. This is just y equals 3. This is a horizontal line at +3. There's only one variable, so it's one of those special cases, and there's not really anything to do here. Domain, you can plug in any x you want because there is no x in the function. This just says no matter what x I plug in, the answer is always 3. The range, though, is different. The range is a single value. We only use y equals 3. So that means it's a single number, not an interval notation. And then this one is constant forever. So it's on its entire domain. Okay. All right, last two examples. Now, we did the difference quotient at the beginning. I always put it in early because sometimes we don't get to this portion in class. But this is really what it is. Like, so you don't have to be able to prove this to anyone or do anything with this unless you go on to calculus. But I wanted you to see where in the world that formula came from. It's two ordered pairs on this blue curve, and they drew what's called a secant line through it. A secant line is a line that cuts through a curve twice, okay? They gave these very random names. They said, hey, this is A on the x-axis, and this is just a little bit further down. They called it A plus a distance of h. And then they said, okay, so this point up here would have a y value of f of a, because that's what we get when we plug in a. And this point would have a y value of f of a plus h. And then they did the slope formula. F of a plus h minus f of a equals a plus, or is over a plus h minus a, and the a's on the bottom cancel. That's where this comes from. So this difference quotient is really the slope of a secant line where we have function notation for the listing for the ordered pairs. So, and again, as you get into calculus, the idea is they shrink this to a single point and make it a tangent line. And that's really where we get into how this connects to calculus. And we talked about getting that instantaneous information of the slope. So, whereas this is more of an average because it's between 2 points. So, you know, this is really laying the groundwork for some later material. But for us, we said it's really just learning how to evaluate this. So we're going to do one more of these. And I gave you a hint when we were in class. I said, you know, they used X instead of A because this is how it would normally appear when we ask you to do the difference quotient. And we assume that H is not 0 so that we're not dividing by 0. Then we're just, remember, evaluating f of x plus h of our function, and then negative f of x of our function, and then we put it into our fraction. So let's work through that one really quick. So if we do f of x plus h, there's only one x in my original function. So I'm going to plug that in as a binomial being squared now. We'll have to write that twice and work it out. So that's negative 2 times x squared plus 2xh, and xh would be 2xh's plus h squared plus 3. Distribute that negative 2 just to the parentheses part. Minus 2h squared plus 3. Okay, so there's the answer for that part. Negative f of x is just taking your function and timesing it by a negative 1. So that's going to make that a positive 2x squared and a minus 3. We take our two answers, which I'll box in for you a little bit just so you can see them. And we're going to plug those into this function up here, this function formula. Two function evaluations, specifically the ones we found over here, all divided by h. So this is negative 2x squared minus 4xh minus 2h squared plus 3. And then you just keep writing plus 2x squared minus 3. Remember, the subtraction symbol was done in the function evaluation. We did that with that. And then we have some cancellations on top, the x squareds, 2x squared and negative 2x squared, and the 3 and negative 3. So on top, we're just left with negative 4xh minus 2h squared all over h. We can factor an h out of the top. So we can cancel that h in the bottom. So our final answer is negative 4x minus 2h. And in calculus, they would say remember I said they shrink the 2 points down to a single point, so they let h approach 0. Once we've gotten it out of the denominator, we can let this become 0, and then this part right here, negative 4x, is something called the derivative of the function. So if you're going to calculus, this is going to be a huge, huge connection point for you. Okay, but for this, all you need to do is two function evaluations, plug them in, work it out, simplify it down. So that's all we expect from you right now. And then this last one is just showing you how to do a linear function. It's the same thing as we did in section 3.3. We just have to pull the ordered pair out of the information they gave us, and our final answer, instead of writing y equals mx plus b, we write f of x equals mx plus b. So we're using function notation. So this, when you see it like this, we kind of alluded to this when we were doing the graphs earlier. This is x and this is y. So this is two ordered pairs, negative 2, 7, and 4, negative 2. So my slope would be negative 2 minus 7 over 4 minus negative 2. So that's going to be plus plus. So this is negative 9 over 6, which reduces to negative 3 halves. So there's my slope. I'm going to use my point slope formula. So y minus 7 equals negative 3 halves x plus 2. If I want, I can distribute this since that's divisible, or I could multiply both sides by 2. Remember, that's also an option. I'll go ahead and distribute this one because it's not too bad. When I multiply it times the 2, the 2's will cancel, so we just get negative 3, and we're going to add over the 7. So that's a negative 3 halves x, and then that would be plus 4. But we want it in function notation, so f of x equals negative 3 halves x plus 4. You should always be able to plug in your other point and check and see if this works. So if I plug in the 4 for x, I should get negative 2 as my answer. So if I plug in 4 here, that'd be half of 4 is 2, times that by negative 3, that'd be negative 6, plus 4 is negative 2. So that function does match with that other ordered pair. And that's it for the 3.4.